that saves me almost $230, which is half the cost of the whole car rental. So what we did was I used my little example here to show you if you thought what was the area underneath the curve 1 over x, you might guess that it's the natural logarithm. It turns out that the book defines the natural logarithm as the area underneath the curve from x equals 1 to x equals some value of x of 1 over x dx, or in this case they use the variable t because the upper limit is x. So you integrate from 1 to some value x. And so if you went to the value x equals e, 2.71828, you'd find out the area underneath the curve is equal to 1. Okay, so this area would be 1 to get you to this point, which kind of leads you to believe that even if you didn't know there was any relationship between natural logarithms and the exponential function, you might say at that point, hey, that's the value for the base for the natural exponential function. So by defining the integral, or the area underneath the curve between, well, in this case, I've taken the limits off because when it comes to indefinite integrals, the arbitrary constant would really take into account the fact that I'm not really showing definite limits. And from a definite integral standpoint, I always take the difference in the value of the antiderivative, so I don't really need to worry about the limits there. This is just to define what is the natural log of x. What is the actual numerical value for the natural log of x? So the natural log of 1, you'd have the same limits. The upper limit would be the same as the lower limit, and from one of those theorems we looked at in chapter 4, we'd say the natural log is equal to 0 because the area underneath a curve that doesn't have any width is going to be 0. We know the natural log of 0 is 0 for one thing. And because we defined the integral of 1 over x dx as being the natural log of the absolute value of x, then we can say that likewise the derivative of the natural log of x is 1 over x. Just like we did it the other way previously, we knew the definition for the derivative, and then we used that to define the integral. Now I'm going to explain this absolute value thing here. So let me do that. Okay. So what we've said is the area underneath the curve. Did I turn this thing on? No. Okay, no, I didn't think I was being that loud. Sorry. Okay, so we said that the natural log was defined as the area underneath the curve 1 over x dx. So this is 1 over x. I mean, just under the curve 1 over x. But we know if we talk about the function f of x equals 1 over x, we also know that there's another part to the curve. It's the one that starts out this way and approaches x equals 0 from the other direction. So what we said was the area underneath the curve from 1 to x, that's going to be equal to the area is equal to the natural log of x. But we also notice over here that we have area involved with the other part of the curve, where x is negative. The problem is that if we remember back to pre-calculus, we can't take the natural log of a negative number. So because of that, we can't say, if we had something like, what is the integral from -3 to -1 of 1 over x dx, we couldn't say it's equal to the natural log of x without the absolute value. Say we did it without the absolute value. If we did that, and then we tried to evaluate the antiderivative at the upper limit and subtracted the antiderivative at the lower limit, you'd say, can't do that. We can't take the natural log of a negative number. But we know there's an area, so what the heck do we do? Well, we find out if we instead of doing this, that's not the correct answer. If we say, what's the integral from -3 to -1 of 1 over x dx, and we say that's equal to the natural log of the absolute value of x, and evaluate that between -3 and -1. So if we plug in the upper limit, we'll have the natural log of the absolute value of -1 minus the natural log of the absolute value of -3. The natural log, so that's the same as the natural log of 1 minus the natural log of 3, because the absolute value of a negative number is the positive version of it. The natural log of 1 is 0, and the natural log of 3 is just whatever it is. Okay, so you get the natural log of 3, or minus the natural log of 3. So now let me just do the same thing but on the positive side, because this area, if I look at the area from here, from -3 to -1, and I compare it from 1 to 3, they should be the same magnitude because they're symmetric curves. They may not look like that just because I didn't draw it that well, but if I were to, sorry, what happened here? Delete. Okay, so if I did the same thing from 1 to 3 of 1 over x dx, then I'd have the natural log of the absolute value of x between 1 and 3. And you can see under those circumstances, the absolute value really doesn't change anything because the absolute value of a positive number is just the positive number. So I'd have the absolute value of, I'd have the natural log of 3 minus the natural log of 1. Natural log of 1 is 0, so I get the natural log of 3. So let's see if this makes sense. So it's saying that we get the same magnitude, the natural log of 3. One's positive, one's negative. Well, that makes sense because we said that the area below the curve is negative and the area above the curve is positive. So by using this as my antiderivative of the integral of 1 over x dx, by putting the absolute value in there, it allows me to find the area underneath the curve in the positive part and in the negative part, and it also gives me the correct sign that it's negative if it's underneath the x-axis and it's positive if it's above the x-axis. So let's just look at a simple example. Let's do an indefinite integral. If I said, what's the integral of 1 over x plus 7 dx? So that's a little bit harder than the one we just did, which is 1 over x. So the way you would do that is you would use u substitution. So you would have u equals x plus 7, du equals dx. Officially it's 1. The derivative of x is 1 times dx. So it's just but it's just dx. So if I make the substitution back in, I'd have 1 over u du. And if you look in your book or you look at the handout I gave you, actually I'm not sure if that was, I think that's in there. If you look that up, it's 1 over, the integral of 1 over u du is equal to the natural log of the absolute value of u plus c, and then you plug u back in, so you get the natural log of the absolute value of x plus 7 plus c. So that's the answer. So anytime you have an integral that's just x plus 3 dx, the answer's the natural log of the absolute value of x plus 3. And we're going to use this a lot, not just in this chapter, but in subsequent chapters. So when you have the integral of, the integral of 1 over x plus or minus some number, it's always just the natural log of x plus or minus that number with the absolute value signs. Okay. Now you could have another one. Here's another simple example. A little more complicated. Let's say I have 2x over x plus 5 dx. No, that's not correct. X squared. Yeah, I could put. Again, and the way you can usually identify whether the problem is going to be a natural log, involve the natural log, is when the term in the denominator does not have a parentheses or does not have a square root. You know, if I had something, don't copy this down, I'm just going to show you, if it was something like this, then I would end up using u substitution and I'd have 1 over u squared du. Or if I had the square root of something like that. But when I have just an expression without the whole thing being squared or square rooted or signed or cosigned, some kind of thing like that. So here I just have x squared plus 5. I don't have x squared plus 5 squared. I don't have the square root of x squared plus 5. So that kind of would lead you to think, oh, it might be the natural log as the solution. So I'm going to let u equal the denominator. So du is going to be equal to 2x dx. And that's exactly what I have up there. So I'm going to make the u substitution. So it becomes 1 over u du. So 2x dx is du, and x squared plus 5 is u. So when you integrate it, you get the natural log of the absolute value of u plus c, and then you plug u back in, and there's your answer. Let's do one more similar to this. You had the integral of, I'm going to make it up here, so let's have x cubed plus, okay, again, the denominator is not squared, it's not the square root, so you say, oh, it might be the logarithm, so I'm going to let the whole denominator be u. So then I take the derivative, I get 3x squared plus 3, this whole thing times dx. And I go back to my original integral and I say, do I have 3x squared plus 3? Well, not exactly, but if I factor out the 3 in my du, I'll get x squared plus 1. And so now I do. So I divide both sides by 3. And now this does match up with that. So then I would make the substitution. So x squared plus 1 dx, x squared plus 1 dx is du divided by 3, and the whole denominator is u. I'd factor out the negative, or the 1/3, and then I'd say, hey, that's in my book. I just use the formula. So the formula says the integral of 1 over u du is the natural log of the absolute value of u plus c. And then I plug u back in. Okay, so that's how polynomials work. One other thing is that, if you remember back to chapter 4, we knew what the integral of the sine and the cosine were, because we knew what the derivative of the sine and the cosine were. But we knew what the derivative of the tangent, secant, cosecant, and cotangent were, but we didn't know what the integral of the tangent was, the integral of the secant, the integral of the cosecant, and the integral of the cotangent. So with the logarithms, we can now come up with the equations for the integrals of those 4 trig functions. So here's the first one. Well, actually, let's start off with the tangent, so I'm going to erase that. So if you have let's say we want to know what the integral of the tangent of x is. We don't have that. We know what the derivative is. It's secant squared, but the integral of the tangent is not the secant squared. The derivative of the tangent is secant squared. So what you would do is you'd rewrite it in terms of the sine and cosine. So the tangent is the sine over cosine, and we'd let the denominator be equal to u. So u is equal to the cosine of x. If we take the derivative of u, that's negative the sine of, well, the derivative of cosine x is negative sine x. We include our dx on the end. We go back to our original integral. What we have is the sine of x dx. So what I'll do is I'll multiply by -1. So I can say that the sine of x dx equals negative du. So now we can make the u substitution. So we get sine of x dx is going to be negative du. And 1 over the cosine is 1 over u. Notice I put this in parentheses, because if I didn't, it would look like it have 1 over u minus du, not 1 over u times negative du. Then you factor out the negative sign, so you get 1 over u du integral. The integral of 1 over u du is a natural log, so we get negative the natural log of the absolute value of u plus c. And the final answer is substituting u back in. So what we can say is the integral of the tangent of x is equal to negative the natural log of the absolute value of the cosine of x plus c. And you could do the same thing for the cotangent. I'm not going to go through every step, but if you do the cotangent of x, the cotangent is the cosine over the sine. And when you go through the whole same operation, you find out that the integral of the cotangent of x dx is equal to positive the natural log of the absolute value of the sine of x plus c. So that's, the reason you don't have the negative sign is because u is the sine in this case, and du is positive cosine of x dx. And so let's look at the other two, which are the secant. So if I want to know what the integral of the secant of x dx is, that's equal to integral of 1 over the cosine of x dx. And you're like, that didn't help me any. What do I do now? Because if I choose the denominator to be the cosine of x, or u to be the cosine of x, there's no du there that matches up. And the way you do it is actually not this way. Okay, you might believe it's this way, so that's not going to work. So let's see if I can remember how to do this. So what you do is you multiply by the secant of x plus the tangent of x, and you divide by the secant of x plus the tangent of x. So I'm just multiplying the numerator and the denominator by the same thing. So if I multiply out the numerator, I'll get secant squared of x plus secant x tangent x. And the denominator just is the term I multiplied it by. Right now it looks like it's just getting more complicated, but if I let u equal the denominator, and then I take the derivative of my chosen u, the derivative of the secant of x, if you look that up in your derivative tables, is the secant of x times the tangent of x, and the derivative of the tangent is secant squared. So derivative of this is that, the derivative of that is that. You can see that the numerator is that. So secant squared x plus secant tangent x times dx is du, and the denominator is u. So with those two substitutions, I'll get 1 over u du. So the integral of 1 over u du is the natural log of the absolute value of u plus c. And then I plug it back in. So what I can say is the integral of the secant of x dx is equal to the natural log of the absolute value of u, which is secant x plus tangent x plus c. So that's another one that you'll find in your tables, the integral of the secant. And not surprisingly, the integral of the cosecant of x is negative the natural log of the absolute value of the cosecant of x plus the cotangent of x. So it has the same kind of format, just like over here. Well, previously, we had the integral of the tangent and cotangent were just similar to each other. One was sine and one was cosine, and one had a positive sign and one had a negative sign. So same thing again, negative sign. That's because the derivative of the cosecant is negative cosecant cotangent, and the derivative of the cotangent is negative cosecant squared. So those two negatives result in a negative here. So now we have the integrals. Because of the definition of the natural log, the integral of 1 over x dx, we were able to find the other 4 remaining trig function integrals. We have increased our toolbox of integrals. Okay. Okay, so now we're going to do a little review of natural log, properties of natural logarithms, and exponential functions too. So this is pre-calculus stuff. So the general exponential function is y is equal to some base number a raised to the variable x. And the corresponding inverse function, the logarithm function, is y equals the log to the base a of x. So you can write the relationship between two numbers, actually 3 numbers, either logarithmically or exponentially. The exponential, especially when you're dealing with whole numbers, or I should say natural counting numbers, is the easiest one to understand, because 2 cubed is just going to be 2 times 2 times 2, 2 times 2 times 2, which is 8. The corresponding logarithm equation says that the log to the base 2 of 8 equals 3. Likewise, if you take a different base, 10, and you raise it to the 3rd power, that means 10 times 10 times 10, which is 1,000. The corresponding logarithmic expression says the log to the base 10 of the number 1,000 is 3. Now, what I always think about is I don't think about it in that term. What I think about is what number do I need to raise the base to get the number in the argument of the log function. So what power do I have to raise 2 to get 8? And the answer is 3. Or in this case, what power do I need to raise 10 to get 1,000? Again, the answer is 3. Rather than thinking of log base 2 of 8 equals 3. What number do I have to raise 2 to get 8? So that's a slide rule, which you may or I think I talked about. Unfortunately, I can't get it to work. It's not sliding. But slide rules use the properties of logarithms to change multiplication into addition. And that was due to we'll come back to that. Anyway, let's just continue on. That was just to remind me of slide rules. So there's a special case of logarithmic and exponential functions. And all it is it's a base that's not a whole number. It's a specific number. It's 2.71828 ... And when you use that number as your base, then we say it's the natural exponential. Usually we drop the natural part, especially when we're dealing with exponential. We just say e to something. So we would say y equals e to the x. We wouldn't say y equals the natural exponential to the x power. We just say y equals e to the x. The interesting things about the natural logarithm function is, well, another one is that instead of saying log to the base e of x, we define a new symbol. We just call it the natural log using ln. All the other exponential and logarithm, well, all the other log expressions, the base is some number. But when the base is e, we use ln, which we call the natural logarithm. The natural logarithm of e is 1. Also, the other key thing that we learned was that if you take e to the natural log of x, it's equal to x, and the natural log of e to the x is x. And when this happens, when f of g of x equals x and g of f of x equals x, so this is back to the concept of inverse functions. So let me add a page. So if f of g of x equals x and g of f of x equals x, f of x and g of x are inverse functions. And we use this concept to be able to solve logarithmic and exponential equations where we have x as an unknown. We're trying to figure out what value of x satisfies the logarithmic or the exponential function. So here are the properties of logarithms. These are key things to remember. If you have you can have two numbers, two functions, anything, two things multiplied together. The natural log of two things multiplied together is the natural log of the first term plus the natural log of the second term. This is what a slide rule does. The scale is set up so that the numbers on the scale are represented by their position in the natural log of the values. And so when you add the two things together using the slide and just using a ruler, basically adding lengths together, the result you get is the multiplication, and then you just do the opposite. You look up the number on the other scale. You can also use a slide rule for subtracting numbers. So you take the original number, show its position on the slide rule in terms of a logarithm, subtract the distance that's associated with the natural log of the second number. That difference gives you the natural log of the quotient, and then you can look up the corresponding number on the scale. The final one is this inverse relationship between the natural logarithm and the exponential function. In this case, I don't have e here. So this works. The natural log of a to the n is n times the natural log of a. It's also the natural log of e to the n is equal to n times the natural log of e. In this case, the natural log of e is 1, so it's equal to n. That's what I showed over here with e to the natural log of x is x, or the natural log of e to the x is x. So it's kind of using that result for that third property of logarithms. And what we're going to do is we're going to use these properties to be able to not do the integral of the 1 over x dx, but for calculating the derivative of the natural logarithm of something, which we haven't done yet. So let's just look at that. So, our rule here, this is the rule, derivative rule. It says the derivative with respect to x of the natural log of x equals 1 over x. Also, the derivative with respect to x of the natural log of the absolute value of x is also equal to 1 over x. So you don't have to have the natural log you don't have to have the argument in absolute values to take the derivative. Even though the integral involves the absolute value, when you take the derivative, it doesn't have to be there to start with. So let's say f of x equals the natural log of x squared. So if I want to find the derivative of this, I'd have to use the chain rule, because I have the derivative of the natural log of x, but I don't have the derivative of the natural log of x squared. So we end up using the chain rule all the time when it comes to taking the derivative of the natural log of some function. So we would say f of u equals the natural log of u, u of x equals x squared. So f prime of u is 1 over u from this equation. U prime of x is 2x from our power rule. The chain rule says f prime of x equals f prime of u times u prime of x. So we plug those back in. F prime of x equals 1 over u, that's f prime of u, times u prime of x, which is 2x. And then you say, okay, I need it all in terms of x, so I go back, find out what u was. So then I substitute that in. So I get 1 over x squared. U is x squared, right there. 1 over x squared times x. 2x. So if you simplify it, you get 2 over x. Now, interestingly enough, it's kind of interesting. The x, one of those x's cancel out. So, this is one way to solve the problem. A lot of times you can use the properties of logarithms to rewrite the original equation in a simpler form so that you can do a simpler derivative. So here's another way. So what you do is you start with the original function, and then you use this property. The natural log of a to the n is n times the natural log of a. So we'll say, but the natural log of a to the n is equal to n times the natural log of a. And a doesn't have to be a number. A can be a function. So in this case, a is x. So I'll say, and for our case, a is equal to x. So my original function I can rewrite as 2, the exponent, raised to the natural log of x. So instead of taking the derivative of the natural log of x squared, I can take the derivative of 2 times the natural log of x. So now I don't have to use the chain rule because I don't have x squared in the argument anymore. So it's just going to be 2, the constant, times the derivative of the natural log of x, which is 1 over x. And I get the answer 2 over x, which is the same answer I got here. Now, if I had something that was a little, it ended up, I saw that, I didn't plan on doing that. So let's look at another example where I can't do that. So let's say it's the natural log of x squared plus 1. In this case, I can't take the exponent out because the exponent is only applied to one term in the parentheses. So again, I'd have to use the chain rule. So I'd say f of u equals the natural log of u of x equals x squared plus 1. Take the derivative. Derivative of the natural log of u is 1 over u. The derivative of x squared plus 1 is 2x. So the chain rule says f prime of x equals f prime of u times u prime of x. Plug those in, you get 1 over u times 2x. So that's that. That's that. And then I plug u back in, and I get 2x over x squared plus 1. So that's the answer. So you can see I can't simplify it. In the previous example, I could simplify it, and I could use the properties of logarithms, but in this case, I couldn't use the properties of logarithms. All I could do is use the definition for the derivative of the natural log of u, and I could use the chain rule, and I came up with the answer. So I'm going to go ahead and, what is this? I have to think about this. Is after Thanksgiving. I'll wait till tomorrow. I'll try to make it so you don't have to study too much over Thanksgiving. So we'll give you this. We'll assign it tomorrow, so it'll be due Tuesday after Thanksgiving.